Describing transformations given graphs. In this video, we're going to look at 3 specific examples where we described what transformation that occurred given graphs and come up with the equations of the transformed functions. Example 5. Determine the equation of g of x by analyzing the transformation from the base function f of x equals to x squared to g of x. So we're given the graphs. We have f of x and g of x. When we analyze transformation of functions, we need to pay special attention to how the origin from the original function transforms. So step 1 is identifying the origin. So right there. In the base function, the origin is the vertex. So we identify the vertex from the image function as well. So step 2, we identify the vertices of quadratic functions. So we have the 2 vertices identified. Now, let's analyze how the origin ends up at the place 2, -1. We will first look at it algebraically to help you understand what happens. Once you understand what's going on, you can do it totally visually without much calculations. If we use mapping notation, we know that the point 0, 0 becomes the point 2, -1. We also know that if we write the mapping notation in general form, we have xy that changes to kx plus d and ay plus c. Since the point xy is now 0, 0, the image point is going to be k times 0 plus d, comma, a times 0 plus c. So notice that the vertical and horizontal stretch or compression doesn't play a factor in how the origin is transformed because it's 0. So when we simplify, our new vertex is going to be d, c. Remember that d represents the horizontal translation, c represents the vertical translation. So visually, we know that the origin has moved 2 units to the right and 1 unit down. No stretch, no compression. Step 3. Next, we pick 9 points from the image function and work backwards. Let's choose the points 1, 3 first. If we apply the transformation slowly, we know that we have from f of x, we have x, y, and then we have a middle curve that has only the stretch or compression. So we have kx, ay, and then it finally translated to g of x, which has kx plus d, ay plus c. So right now, when we work backwards, we're trying to figure out the curve in the middle with only the stretch or compression, without any translation. So let's work it out algebraically first. So let's say the point on f of x is x subscript 1, y subscript 1. When we transform it at first, with stretch or compression, we have k multiplied by x subscript 1 and a multiplied by y subscript 1. And then when we transform it again with the translation, we end up at the point 1, 3. Now, since that we know that d is 2 and c is -1 from working with the vertices, we can work backwards and solve for k x subscript 1 and ay subscript 1. So we know that kx subscript 1 plus d equals to kx subscript 1 plus 2, which equals to 1. And then when we solve for k x subscript 1, we have -1. When we solve for ay subscript 1, we know that ay subscript 1 plus c equals to ay subscript 1 minus 1, which is 3. So ay subscript 1 equals to 4. So the unknown point is -1, 4. Now it looks pretty complicated. So now let's look at the graph visually and do it much faster. Because we know that D is 2 and C is -1, we can undo the vertical translation first. So we can go up 1 from the point 1, 3, and then we go left 2 units. And there we are. We are now at the point -1, 4. We don't really need to solve equations. Now let's pick one more point from g of x and work backwards. So let's choose a point 3, 3. So if we apply the transformation slowly, just like the previous one, we have this formula again, okay, showing us how to transform using mapping notation. This time, instead of working with x subscript 1 and y subscript 1, we have x subscript 2 and y subscript 2. And then we have our image point being 3, 3. And then solving these equations again, just like the previous point, we get the point 1, 4. However, this is a little bit time consuming, so if we do it visually, we know that because of the D and C, okay, D being 2 units moving to the right and C being 1 unit down from f of x. So now we start with g of x, we do the opposite, so we go up 1, okay, and then we go to the left twice, and we have a final point. So now let's focus on this curve that is in the middle, that is not f of x and not g of x. So we're going to connect the points, okay, the vertex, and then the 2 points that we calculated. Before we do the next part, we need to remember that for the vertex, we have 0, 0 at the beginning. For the middle curve, it's still 0, 0. And then for g of x, the vertex was 2, -1. So now we have the following. We can focus on starting from f of x, and we want to transform to the stretch or compression. So we could have a horizontal stretch or compression by a factor of k. We can also have a vertical stretch or compression by a factor of a. What we know so far is that starting from the point x subscript 1, y subscript 1, we end up at the point -1, 4. Starting from the vertex 0, 0, we end up at 0, 0. If we started from the point x subscript 2, y subscript 2, we end up at 1, 4. Now we need to remember that for quadratic functions, we can combine vertical stretch or compression with horizontal stretch or compression to obtain a new vertical stretch or compression. Sounds complicated, but it's actually easier to work with. So what it means is that we can change the mapping notation. Forget about the horizontal stretch or compression and just look at the question as if you only have vertical change. So let k be 1, and then let's say we have a subscript 2 this time. It's a different value than what we have on the previous slide because now we have combined the vertical change with the horizontal change to get a new a. So look at our 3 points again. So if x hasn't changed, then it means that x subscript 1 is -1 and x subscript 2 is 1. Now all of a sudden we have values to work with without needing to solve equations. So let's look at the graph now. So if I draw a vertical line that crosses both curves, okay, why do I want a vertical line? Because I'm looking at the vertical change. Because I just said I'm going to assume that there's no horizontal stretch or compression. I'm only focusing on the vertical stretch or compression. So now we can see that on f of x, okay, we have x subscript 1 where it is -1. So that means we have the point -1 and 1. Now at the other side, we can draw another vertical line so that x subscript 2 has a value of 1. So that's the point 1, 1 on f of x. Now why do I want to do that? So let's look at the distance from the points -1 and 1 to the x-axis. Okay, it is 1 unit long. And then the distance from the x-axis to the point on the purple curve, okay, the one that is in the middle, that is the curve that is neither our original curve nor our image curve. It is the curve in between. It is 4 units long. Now what does it mean? 1 unit versus 4 units. Now remember that we are talking about a vertical stretch or compression, and this a subscript 2 is supposed to multiply to y, so it's a multiplication. So that means that a subscript 2 is 4 times the original value, which is 1 unit, because 4 times 1 gives us 4. So a subscript 2 is 4 units. Do not perform subtraction because this is a multiplication. So now we can come up with a final equation. G of x equals to a subscript 2 multiplied by, open bracket, x minus d, close bracket, squared, plus c. So substituting our a subscript 2, d, and c into this equation, we have g of x equals to 4 times, open bracket, x minus 2, close bracket, squared, and then subtract 1. So comparing all 3 graphs together, you can see before, which is f of x, middle curve, not named, and then we have a final curve which is given to us as g of x. Example 6. Determine the equation of g of x by analyzing the transformation from the base function f of x equals the square root of x to g of x. So first step, we are going to identify the origin, because if we have the origin in the original function, we can figure out the translation right away. So since we have found the origin, which is the starting point of a square root function, we are going to find the starting point of g of x as well. So for square root functions, you want to identify the starting points. So next, we're going to analyze how the origin ends up at the points -2 and 3. So just like the previous example, we can do it algebraically and figure out that there's only translation happening. So we found out that the horizontal translation is 2 units to the left, and the vertical translation is 3 units up. So when you look at the point, the numbers are right there in front of us, d and c. d is -2, c is 3. Now in step 3, we're going to pick nice points that we can work with. If we look at g of x, unfortunately, there's only one nice point that we can work with, and it's the point -5, 4. So we want to undo the translation. So we could apply the math that we did algebraically from the previous question and do all these calculations to figure out that we have the points -3 and 1. We could do that, but that takes a little bit long. So let's do it using the shortcut. So since we know the horizontal change is 2 and the vertical change is 3, I'm going to take the point -5, and 4, I'll move the point 2 units to the right and 3 units down, and that's my new point, which is exactly the same thing as what I would have calculated algebraically. So my new point is -3, 1. Now we're going to draw a curve connecting the 2 points. So this is my intermediate curve if I undo the translation. So let's take away the final curve so that there's less work on the screen, so it's less confusing. So now I want to focus on this intermediate curve, and I want to work backwards more. Now, because this question has reflection, so at this point, I need to undo the reflection before I can look at the compression or stretch. So I am going to undo the reflection. So from the point -3, 1, it is 3 units away from the y-axis. Okay, so if I count 3 units from the y-axis to the right, that would be the reflection of that intermediate curve that is already on the grid. So I add that extra point, and now I'm going to join the origin with my new point. So that's the curve that I want after undoing the reflection. Now I get rid of the other curve because it's just in the way. So now I can focus on finding the stretch or compression. So a vertical stretch or compression can be a combination of another vertical stretch or compression with a horizontal stretch or compression. So that was from a parabola example earlier. So there are different ways to find the stretch or compression for square root functions. Method 1, let's find vertical stretch or compression. Okay, so there's one method. So if I look at it vertically, then I can find a point on f of x that is along my guideline right now. Okay, this is just a visual guideline that I add for myself. So then I can compare the 2 points. So from this, I can try to solve for a. Okay, so I know that a multiplied by y should equal to 1 because 1 is the y-coordinate of my intermediate curve. And the y-coordinate of f of x right now is actually not very clear because I need to estimate it at first. I don't know if it's 1.8, 1.7, or 1.7 something. I don't really know. So it is an estimate. So maybe I don't really want to look at this using a vertical stretch or compression. So I'm going to look at it using method 2. I'm going to check if I have horizontal stretch or compression instead. So I'm going to draw a horizontal line mentally and check. So I can draw a point on f of x. And now I get rid of everything else. Now this time both points are nice points, they're integer points, so it's easier for me to work with. So I want to solve for k in kx equals to 3. and we are given that x equals to 1. So remember, kx is the x-coordinate of the intermediate curve. X is the coordinate for f of x. So that means k must be 3, if I do it algebraically. We can also do this visually. So from the y-axis until the point on f of x, that is 1 unit horizontally. And then from the from the y-axis to the point on the intermediate curve, there are 3 units horizontally. So this is a factor of 3 comparing the 2 arrows. Now method 3 means that we can use a combination of vertical and horizontal stretch or compression, and this method is used for more complicated questions where you actually get estimates when you only use the horizontal stretch or compression, or if you only use vertical stretch or compression. So method 3 doesn't really apply to this example here. So our final equation, okay, for g of x. So a was not being used because we didn't analyze it using a vertical stretch or compression. So a is 1. Now k was 3, so 1 over k is 1/3. D is -2, so we have x plus 2 inside the bracket. And then c is 3, so we add 3 at the end. When there is reflection, we end up using 2 extra functions to help us figure out the equation of g of x. Example 7. Determine the equation of g of x by analyzing the transformation from the base function f of x equals 1 over x to g of x. So we're given the graphs of the 2 functions. Some of you might think that looks messy, so we're going to start analyzing it. However, since this is our last example, we're going to do this visually only. I'm not going to provide you with the algebraic steps in this case. So step 1, we want to undo the translations. That's what we did with the other 2 examples. Step 2, we're going to undo the reflection. That's what we did in example 6. And then lastly, we're going to find out the stretch or compression, whether it is horizontal or vertical. So first, undo the translation. So remember, for the other 2 examples, the first thing that I did was I identify the origin. So identify the origin. I use an empty circle because this point is not part of the curve. So I use an empty circle to indicate it's not an actual point. It's just something that I'm using for the analysis. And then we would realize that this point is the intersection of the asymptotes. So then we identify the intersection of the asymptotes of g of x. So there's my point. And we notice from f of x to g of x, the translation is 1 unit up and 2 units to the right. Okay, so let's get rid of the asymptotes now that we don't need them anymore for now. So we can see that it's 1 unit up and 2 units to the right. So next, I try to pick up a few nice points from g of x. So there are some nice points that I can use. So then I am going to undo the translation, which means for each point that is on g of x, I'm going to move them 2 units to the left and 1 unit down, like so. So I do it to all 4 of them, and then I draw my new dots. So those So I have my new intermediate step. So I have these points. So I can join the points using nice curves. Why? Because right now the asymptotes for my intermediate curve are the same asymptotes as f of x. So I don't need to draw new asymptotes. It's already on there. So now I have the curves. So to make things easier to read, let's get rid of g of x totally. So now we're going to undo the reflection. Because right now we know that there's reflection happening because the curves, the f of x is not on the same quadrant as the intermediate curve right now. Similar to the previous example, example 6, sometimes we can look at things both horizontally and vertically. So if I look at the reflection as a reflection in the x-axis, then that's how I get my new points. Okay, so I reflect them vertically to get a new intermediate graph. I can also look at the reflection horizontally to get this exactly same points. So this is a special property of reciprocal functions. Okay, so a reflection in the y-axis means the same thing as a reflection in the x-axis if the base function is f of x equals to 1 over x. So then I can draw my new curve, get rid of the other one. So now I have my stretch compression. So method 1, I can look at it vertically. So I'm going to look at the integer points first. Notice some of them are not integers and they're more difficult to read. So I'm going to pick 2 points on the same vertical line that are integers. So I have the point -1, -1. After the transformation or after the stretch, it became -1, -3. I also have another point started from 1, 1 and then end up at 1, 3. So that means we have a vertical stretch by a factor of 3. And then we can check with the remaining points. I started with -3, so now I can pretty much guess it must be -1/3. After the transformation, I have the point -3, -1. And then for the last set of 2 points, we have 3, 1/3, and it became 3, 1. And then we are done. Okay, so with all the curves on the graph, it looks quite messy. However, when you're working on it visually, sometimes that's how many curves you actually have to draw. Let's work out the equation of g of x. So the general equation for a reciprocal function that has been transformed is g of x equals to a over 1 over k bracket, x subtract d close bracket, and then plus c. We found that a is 3 because it's a vertical stretch by a factor of 3. And then k is 1 because we didn't even look at it. And then d is 2 and c is 1. So when we substitute, our final equation is g of x equals to 3 over x subtract 2 and then plus 1. That's using method 1. And our asymptotes are x equals to 2 and y equals to 1. Method 2. This time we're going to look at horizontal stretch or compression. So look at my horizontal lines this time. Similar to method 1, some of the sets we have integer points, some we don't. So let's focus on the integers first. If I start from the point -1 and -1, this time I end up at -3, -1. If I look at the point 1, 1, this time I end up at 3, 1. So when we look at it closely, we will realize that this is a horizontal stretch by a factor of 3. Checking with the other two sets of points, the point -1/3, -3 would give us the point -1, -3 after the horizontal stretch. For the other one, we start from 1/3, 3, and we end up at 1, 3. So working out the equation of g of x, we have the same general form as method 1. This time a is 1 because we didn't do anything for the vertical stretch or compression, and k is 3. So it means we have g of x equals to 1 over 1/3 multiplied by bracket of x minus 2. And then we add 1 at the end. Simplifying the equation, I have the same thing as method 1. G of x equals to 3 over x minus 2 plus 1. And we also have the same asymptotes. X equals to 2 and y equals to 1.